China's latest energy breakthrough did not begin with a dramatic announcement or a flashy global unveiling. It began quietly, inside a research facility outside Shanghai, where engineers pushed a solar cell beyond an efficiency level that conventional silicon panels have never really been able to reach. And the important part is not just that they broke a number, it is how they broke it. They did not rely on some exotic material that exists only in theory or in a handful of impossible lab samples. Instead, they placed a newly engineered crystal structure, one that can be produced for a fraction of the cost of traditional solar cells, directly on top of ordinary silicon. That single move changes the conversation completely, because it does not just improve the panel, it changes the ceiling. That is the real significance here. This is not a small step forward, and it is definitely not the kind of progress that only matters in a scientific paper. It points to a fundamentally different upper limit for how much electricity can be extracted from a single ray of sunlight. And for anyone who has spent years working in solar engineering, chasing tiny improvements by fractions of a percentage point, that kind of result is deeply uncomfortable, because it suggests that while much of the world is still refining the same silicon panels that have dominated rooftops for roughly 40 years, China is building the technology that could eventually replace them. To understand why this matters so much, you have to understand the barrier that has shaped solar power for decades. For most of the history of the industry, engineers have been fighting against a stubborn physical limit known as the Shockley-Queisser limit. The name sounds technical, but the idea is simple. A single layer of silicon can only absorb and convert a certain portion of the sun's light efficiently. Sunlight is not one uniform thing. It is made up of many different wavelengths, and a single semiconductor can only make real use of part of that spectrum. The rest either passes through the material unused or is turned into waste heat instead of usable electricity. That is why silicon solar cells, even after years of improvement, have always had a ceiling they cannot naturally escape. The conventional single-junction panels that cover rooftops and blanket huge solar bases across regions like Inner Mongolia and the Gobi have spent decades creeping toward a theoretical maximum efficiency somewhere in the high 20s. Yet the commercial panels people actually buy today still mostly sit in the low to mid-20s. That means the industry is still nowhere near the physical limit, even after all this time. But more importantly, it means that the problem is not simply one of better manufacturing or cleaner factories. You cannot build your way around a limit that is baked into the physics of using just one material to capture the full solar spectrum. Every wavelength of light carries a different amount of energy. A semiconductor that is great at converting one band of light is not automatically good at converting all the others. Some of the energy is wasted as heat, and some of it is not absorbed at all. So for decades, the solar industry tried to solve the problem in the most familiar way possible. Make silicon panels a little cheaper, make them a little more efficient, and keep squeezing out tiny gains year after year. It was a slow, careful march forward. The same way phone makers once chased marginal improvements in camera megapixels, solar manufacturers kept polishing the same basic formula. China decided that was not enough. Instead of polishing silicon forever, it started stacking another material on top of it, one that could capture the part of the spectrum silicon tends to miss. That shift is what makes this story different. It is not about doing the old thing slightly better. It is about changing the architecture of the solar cell itself. And the reason this has drawn such attention is because the ceiling has been stubborn for the entire industry. The Shockley-Queisser limit was first calculated back in 1961. Since then, 6 decades of relentless research have gone into trying to beat it. Billions of dollars have been spent. Some of the smartest materials scientists in the world have worked on the problem. Yet single-junction silicon cells have never truly broken through. They have only kept inching closer. So when a technology appears that can bypass that limit rather than slowly approaching it, it is not just a better version of the same old panel. It is a different class of device entirely. The material making this possible is called perovskite. If that word sounds familiar, it is because it originally referred to a naturally occurring mineral discovered in Russia's Ural Mountains in the 1830s. It was named after a Russian mineralogist, and for more than a century it sat quietly in geology textbooks, noticed mostly by specialists. But the important part for solar technology is not the original rock itself. What matters is the crystal structure. That arrangement of atoms turns out to be almost perfectly suited for absorbing sunlight and turning it into electricity. Even better, That structure can be recreated synthetically using a whole family of chemical compounds. That is where the real opportunity begins. Unlike silicon, which has to be melted at extremely high temperatures, purified to an extraordinary degree, turned into wafers, and then cut through energy-intensive industrial processes, perovskite can be grown from a liquid solution. In practical terms, that means it can be deposited onto a surface in a way that looks much closer to printing than to traditional semiconductor manufacturing. Instead of giant furnaces, wafer slicing, and heavy material processing, you can imagine a method that is far simpler, faster, and potentially far cheaper. That manufacturing difference matters a lot. It means the production cost could drop dramatically because you are cutting out a large portion of the most energy-heavy and expensive steps in conventional silicon panel manufacturing. But the real breakthrough comes when perovskite is not used as a replacement for silicon, but as a partner to it. When you stack perovskite on top of a standard silicon cell, the two materials can divide the work. Perovskite is especially good at capturing the higher energy, shorter wavelength portion of sunlight, including the blue and ultraviolet end of the spectrum. Silicon underneath then handles the longer wavelength red and infrared light that perovskite does not absorb as efficiently. Put those two layers together, and you get what is known as a tandem cell. In simple terms, it allows the panel to harvest two different slices of sunlight in the same footprint, which is exactly how it blows past the theoretical ceiling that limits any single material solar cell. This is where Chinese research groups and manufacturers have moved especially fast. Major players like LONGi, along with several Chinese laboratories, have been pushing these perovskite silicon tandem cells toward record-setting efficiency. Some certified lab results have climbed well past 30%, and some experimental designs have reportedly pushed beyond 33%. Just a few years ago, those numbers would have sounded unrealistic for silicon-based technology. Now they are becoming the benchmark for the next generation. And every small gain matters more than most people realize. A difference of even a fraction of a percentage point becomes enormous once you spread it across solar farms that cover desert landscapes the size of entire cities. That is why these breakthroughs are not just impressive on paper. They have genuine real-world consequences if they can be produced at scale. The origin story makes the whole thing even more remarkable. A mineral first dug out of the Ural Mountains and named after a Russian nobleman sat quietly in geology collections for generations before anyone realized that its crystal structure was almost perfectly tuned for modern solar power. Nobody in the 1830s could have imagined that this obscure mineral name would one day be tied to the future of renewable energy. Yet that is exactly what is happening now. A material that once belonged to geology is now shaping the next chapter of electrical generation. And that leads directly to the biggest question of all. If the technology is this promising, why has it taken so long to matter? The answer is not just about physics. It is about durability, manufacturing, and whether a lab discovery can survive the transition into the real world. A record efficiency number by itself does not change the world. That is the trap a lot of promising energy technologies fall into. They look extraordinary inside a research lab, under perfect conditions, with careful handling and ideal testing environments. Then, the moment anyone tries to turn them into a real product, the whole thing starts to fall apart. That is why so many solar breakthroughs have generated excitement for years without ever becoming something people could actually buy, install, and trust for decades. And this is exactly where China's approach to perovskite begins to separate itself from the rest. The economic logic here is unusually strong, especially once the manufacturing side is solved. A tandem solar cell that can deliver 30% plus efficiency from the same panel footprint as a conventional 22% silicon panel gives you a major advantage immediately. You are not changing the roof, the field, or the amount of land available. You are simply getting much more electricity from the same space. For a country that has already been building solar bases in deserts on a massive scale, that kind of gain is extremely valuable. It means more output from the exact same land, which matters a great deal when land itself is one of the hardest things to expand at scale. And then there is the cost side, which may be even more important over time. Perovskite is genuinely cheap to produce compared with the process of growing and slicing silicon ingots. So if manufacturers can successfully mass-produce tandem cells at a cost that is only slightly higher than ordinary silicon panels, while still delivering dramatically better efficiency, the cost per watt of generated electricity could fall in a way that undercuts much of the current market. That combination is rare. In most industries, you usually have to choose between cheaper or better. Here, the possibility is to get both at once. That is why the land use angle matters so much. In places like the Gobi or the Kabuchi Desert, where China has already built enormous solar installations, the land, the mounting systems, the wiring, and the maintenance infrastructure are fixed costs. They are already part of the project, whether the panel is 22% efficient or 32% efficient. If a tandem panel produces 30% more electricity from that same footprint, then the country is essentially getting the equivalent of a much larger solar farm without needing more land or more transmission lines. That is not a minor improvement. It is a serious advantage in any country trying to scale up solar while running into the practical limits of land and grid expansion. But here's the catch. None of that matters if the material cannot survive the real world. And that has been the biggest problem for perovskite from the beginning. The challenge is almost frustratingly basic compared with the advanced physics involved. Perovskite crystals have historically been very poor at surviving moisture, oxygen, heat, and ultraviolet light. Those are not niche conditions. Those are the exact conditions every solar panel installed outdoors must face every single day. A solar cell that performs beautifully for a few days in a lab is not useful if it starts breaking down in normal weather. Early perovskite cells degraded quickly when exposed to the environment. Some lost significant efficiency within weeks or months. That would be unacceptable for any technology meant to sit on a rooftop for 20 or 25 years producing steady power. Silicon, by comparison, has a strong record of durability. That is one reason it has remained dominant for so long. Manufacturers can offer long warranties because the material itself is stable enough to justify them. Chinese researchers have spent the last several years attacking this stability problem from multiple angles at the same time. One approach has been encapsulation. That means sealing the perovskite layer inside protective barrier films so moisture and oxygen cannot easily reach the sensitive crystal structure beneath. Another approach has focused on the chemistry of the material itself. Scientists have been changing the composition of the perovskite crystal, swapping different elements in and out of the lattice to make versions that resist heat and light more effectively from the inside. That matters because the goal is not just to protect the material from the outside. The goal is to make the material itself tougher. Some of the newer tandem cell demonstrations from Chinese labs have reportedly kept most of their original efficiency after accelerated aging tests that simulate years of outdoor exposure in a much shorter period of time. That is a major milestone because it suggests the durability gap that kept the technology stuck in research for so long may finally be starting to close. And that gap is important to understand. For years, solar researchers had a running joke about perovskite. The cells could look incredible on the day they were made, then seem like they had aged 20 years after just a short stay in a humid environment. That contrast between stunning lab results and poor real-world longevity is exactly why perovskite remained trapped in papers and presentations for so long. It kept appearing as a future possibility, but never quite became a product people could trust at scale. Closing that gap is not a side note. It is the central challenge that determined whether this technology would remain a scientific curiosity or become a genuine competitor to silicon. Without stability, the record efficiencies do not matter. With stability, the entire market begins to shift. That is also why the recent progress matters so much. Chinese teams are not only pushing the efficiency numbers upward, they are solving the problem that kept the technology from crossing over into actual deployment. And in solar power, that is the difference between a headline and an industry. A lab record is exciting, but by itself, it does not transform an energy system. That is where so many technologies get stuck. They produce a headline, draw attention for a few weeks, and then disappear because the jump from a controlled experiment to a real industrial product is much harder than people expect. The challenge is not just proving that something can work once. The challenge is proving that it can work reliably, cheaply, and at scale. This is where the economic case for perovskite silicon tandem cells starts to become genuinely hard to ignore. If you can produce a panel that reaches more than 30% efficiency in the same physical footprint as a conventional silicon panel that sits around 22%, you are immediately getting more electricity from the same amount of space. That might sound like a technical detail, but in the solar industry, space is money. The same rooftop, the same field, the same solar farm, the same desert site suddenly becomes much more productive without any change to the land itself. For a country like China, which has already built enormous solar projects across desert regions, that matters enormously. Every square meter of land already committed to solar becomes more valuable if each panel on that land produces a higher yield. It means the country can keep expanding output without constantly needing to find fresh territory for every new round of growth. In a sector where land, wiring, and grid connections all become major bottlenecks, that kind of efficiency improvement is not small. It is strategic. The cost argument is just as important. Perovskite is much cheaper to produce than silicon ingots, which have to be grown, refined, and cut through expensive industrial processes. If the tandem manufacturing process can be brought to market at only a modest extra cost compared with existing silicon panels, then the cost per watt of electricity could drop sharply. That is the point where a new technology stops being a science project and starts threatening the market position of the old one. Higher efficiency and lower cost at the same time is a rare combination. When it happens, it usually changes the direction of an entire industry. The land use advantage becomes even more obvious when you look at desert solar bases. In places like the Gobi or the Kubuchi, the land, mounting structures, wiring systems, and maintenance teams are all already part of the cost structure. If a tandem panel delivers 30% more electricity from that same footprint, the result is almost like adding a second layer of value to every project without actually expanding the site. You are getting a much larger solar farm's output from the exact same infrastructure. For a country that is approaching practical limits on how much desert it can dedicate to solar, that is a very big deal. But that still leaves the biggest problem of all. Can the material survive the real world? That has been the central weakness of perovskite from the very beginning. As promising as the material is, it has historically been fragile. Moisture, oxygen, heat, and ultraviolet light have all been major enemies. And those are not unusual conditions. Those are exactly the conditions outdoor solar panels are expected to face every day for years on end. If a material works beautifully inside a lab but breaks down quickly outside, it has no chance of becoming a serious commercial product. Early perovskite cells were notorious for this. Some samples lost efficiency quickly after exposure to the environment. A panel that degrades within weeks or months is useless for real deployment, no matter how impressive its starting efficiency may be. Silicon's biggest advantage has always been its stability. It lasts. It survives weather, heat, sunlight, and time far better than early perovskite formulations did. Chinese researchers have spent the past several years attacking that instability from more than one direction. One approach has been encapsulation, where the sensitive perovskite layer is sealed inside barrier materials designed to keep out moisture and oxygen. Another approach has focused on the chemistry of the perovskite itself, changing the atomic mix inside the crystal lattice to create versions that are naturally more resistant to heat and light damage. In other words, the strategy is not just to protect the material from the outside, but to make the material itself stronger from within. That work is starting to pay off. Some of the newest tandem cell demonstrations out of Chinese labs have reportedly retained most of their original efficiency after accelerated aging tests meant to simulate years of outdoor exposure in a much shorter time. That is a major step forward, because it directly addresses the issue that has kept this technology from crossing over into the commercial world. For years, the story of perovskite was always the same. Incredible lab performance, but too little durability. If that gap closes, the entire future of the technology changes. The reason this matters so much is that solar researchers have long seen perovskite as a material with enormous promise, but poor staying power. The running joke for years was that a perovskite cell could look incredible on the day it was created, and then behave like something decades old after only a short time in a humid environment. That joke existed because the problem was real. The gap between headline efficiency and practical longevity was exactly what kept this technology from becoming a product. Closing that gap is not a minor technical correction. It is the central challenge that determines whether the technology stays in the lab or enters the marketplace. And right now, Chinese research teams appear to be making the most visible progress in solving it. Of course, none of this progress would matter if the technology could not be manufactured at the scale that actually moves an energy grid. A result in a lab is one thing. A result that can be repeated across factory lines at commercial volume is something else entirely. That is where China's industrial strength becomes one of the biggest reasons this story matters. The country has already spent more than a decade building a dominant position in conventional silicon solar manufacturing. That existing base is now being used as the launch pad for perovskite silicon tandem cells. Several Chinese manufacturers have already set up pilot production lines for this next generation of solar technology, and they are treating it not as a side project, but as the natural next phase of an industry they already control in depth. That matters because the infrastructure does not have to be invented from scratch. The silicon wafer factories, the panel assembly lines, the testing labs, the certification systems, and much of the supply chain already exist at enormous scale. That gives China a major advantage. Adding a perovskite deposition step to an existing silicon line is a much smaller jump than building an entirely new solar industry from the ground up. In other words, China is not trying to start over. It is retrofitting the world's biggest solar manufacturing base. And in industrial terms, that is a huge difference. Some of these pilot facilities are already talking about gigawatt-scale annual production within the next few years. That is the point where the technology stops being a laboratory curiosity and starts becoming a genuine commercial competitor. Once production reaches that level, tandem cells are no longer just impressive because of their efficiency numbers. They begin competing on price, availability, and consistency, which is where the real battle in solar is actually fought. Getting from a tiny record-breaking sample to millions of reliable full-size panels is where many promising technologies fail. It is one thing to make a cell the size of a postage stamp perform beautifully once. It is another thing to make the same result happen repeatedly across an entire production run. That is the gap. China's existing manufacturing system is especially well positioned to close faster than most of the world. There is also a workforce angle that rarely gets enough attention. When you retrofit an existing silicon production line to include perovskite, you are not asking engineers and technicians to learn a completely unfamiliar process from zero. The people working there already understand the factory, the equipment, the quality control, and the production rhythm. They are adapting a system they know instead of trying to build a new one from scratch. That kind of experience is difficult to measure on a spreadsheet, but in practice, it can make a huge difference in how quickly a technology matures. And the potential here goes far beyond standard rooftop panels. Because perovskite can be deposited as a thin film instead of requiring a rigid silicon wafer, it opens the door to solar applications that traditional panels were never physically able to reach. Flexible, lightweight perovskite films could be used on curved surfaces, vehicle exteriors, and building facades. In other words, surfaces that were never considered solar real estate could suddenly become part of the power system. One of the most interesting uses is building integrated photovoltaics. Instead of treating solar as a separate add-on installed after a building is finished, the solar generation itself can be built into the structure. That means windows, exterior wall surfaces, and architectural glass could all become part of the energy-producing system. Some Chinese research groups are already working on semi-transparent perovskite cells designed for windows, allowing visible light to pass through while still collecting a meaningful amount of sunlight to generate electricity. Imagine an entire skyscraper facade quietly helping power the building from the inside of its own design. Vehicle-integrated solar is another frontier that suddenly looks more realistic because of this material. China is already a major force in electric vehicles, so the idea of putting a lightweight, flexible perovskite layer on a car's roof, hood, or body panels has obvious appeal. In theory, that could extend range by trickle charging the battery while the car sits in a sunny lot. It would not turn the vehicle into a full solar-powered machine, but it could still add real utility without the weight and rigidity that made vehicle solar mostly impractical before. None of these applications are fully mainstream yet, but the flexibility of thin-film perovskite is what makes them possible for the first time. It also brings an installation advantage that is easy to overlook. Traditional silicon panels are rigid, heavy, and need mounting systems that add cost and structural complexity. A lightweight perovskite film could potentially be attached directly to a roof, a wall, or even a curved feature without the same kind of reinforcement. That is a big deal for older buildings, which were never designed to carry the weight of a conventional solar array. It opens up retrofitting opportunities that simply did not exist before. None of this progress matters if the technology cannot actually be manufactured at the scale needed to change a national grid. That is where China's existing industrial base becomes a decisive advantage. The country has spent more than a decade building a dominant position in conventional silicon solar manufacturing, and now that same machine is being adapted for perovskite silicon tandem cells. In practical terms, that means China is not trying to invent an entire new solar industry from scratch. It is upgrading one it already controls. Several Chinese manufacturers have already started pilot production lines for this next generation of solar technology. They are not treating it like a laboratory curiosity or a long-shot research project. They are treating it like the next stage of an industry they already understand better than almost anyone else. And that matters because the foundation is already there. The wafer production, the panel assembly, the testing labs, the certification systems, and the supply chains behind all of it already exist on a massive scale. That gives China a very different kind of advantage from a country that would need to build all of that infrastructure from zero. Adding a perovskite deposition stage to an existing silicon line is a much smaller jump than creating a brand new solar manufacturing ecosystem. China is essentially retrofitting the world's largest solar production base rather than replacing it. In industrial terms, that is a huge head start. Some of these pilot facilities are already discussing gigawatt-scale annual production within the next few years. And that is the point where the conversation changes. Once manufacturing reaches that level, tandem solar cells are no longer just interesting because of their lab efficiency. They start competing in the real market on price, availability, and consistency. That is where solar technology either survives or disappears. The hard part is always the same: getting from a tiny record-setting sample to a product that performs reliably in millions of units. It is easy to make one impressive cell in a controlled environment. It is much harder to make that same result repeatable at factory scale, over and over, without quality drifting. That is exactly the gap China's existing manufacturing system is in the best position to close. There is also a workforce advantage hidden inside all of this. When you retrofit an existing silicon production line to handle perovskite, you are not asking engineers and technicians to learn a completely foreign process. They already know the factory, the equipment, the logistics, and the quality control standards. They are building on a system they understand instead of starting over from a blank slate. That kind of familiarity is difficult to measure, but in practice, it can make a real difference in how fast a technology matures. And the possibilities go far beyond the standard solar farm. Because perovskite can be deposited as a thin film rather than requiring a rigid silicon wafer, it opens the door to applications that conventional panels were never able to reach. Flexible, lightweight perovskite films could be placed on curved surfaces, vehicle exteriors, and building facades. In other words, surfaces that were never considered part of the solar economy could suddenly become power-generating assets. One especially interesting use is building integrated photovoltaics. Instead of treating solar as something you bolt onto a building after construction is finished, the technology could be built directly into the structure itself. That includes windows, wall surfaces, and architectural glass. Some Chinese research teams are already working on semi-transparent perovskite cells designed for windows, so that visible light can still pass through while the material captures enough sunlight to generate useful electricity. A glass tower could, in theory, help power itself without any obvious rooftop array. Vehicle-integrated solar is another frontier that starts to look more realistic with this kind of material. China is already a giant in electric vehicle manufacturing, so the idea of placing a lightweight, flexible perovskite layer across a car roof, hood, or body panel is especially relevant. In theory, it could extend driving range by trickle charging the battery while the vehicle sits parked in the sun. It would not replace charging infrastructure, but it could add a useful layer of energy capture without the weight and rigidity that made this concept impractical for years. None of these applications are fully mainstream yet, but the flexibility of thin-film perovskite is exactly what makes them possible for the first time. And there is another advantage here that often gets overlooked: installation. Silicon panels are rigid, heavy, and require mounting systems that add cost and structural complexity. A lightweight perovskite film could potentially be attached directly to a roof, a wall, or even a curved design feature without the same reinforcement. That matters a great deal for older buildings, which were never designed to support the weight of a conventional solar array. So this is not just about producing more electricity from solar farms. It is also about expanding where solar can be used at all, and that makes the technology much more disruptive than a simple efficiency upgrade. This is where the global market impact starts to become impossible to ignore. Perovskite solar technology is not only about better lab numbers or even better panels, it is about control over the next major phase of the solar industry. If this technology scales the way China appears to be positioning it to scale, the country that already dominates silicon solar manufacturing could extend that lead into the next generation as well. That matters because the global solar market has been built for years around one basic assumption: silicon would remain the standard. Every major supplier, every factory line, every supply chain decision has been shaped by that reality. But tandem solar cells threaten to change the rules. If they deliver higher output from the same amount of space, and if they can eventually be produced at a competitive cost, then they are not just a niche upgrade. They become the next commercial benchmark. That is the moment old manufacturing advantages either evolve or get left behind. China is unusually well positioned for that shift because it already controls the overwhelming majority of the solar supply chain, from polysilicon refining to wafer production to module assembly. In a market where manufacturing scale matters as much as scientific innovation, that is a powerful advantage. If the next solar standard is perovskite silicon tandem, the country that owns the largest and most adaptable production base is in the best position to turn that standard into a business reality before anyone else can catch up. This is also part of a broader strategic pattern. China has not been betting everything on a single energy technology. It has been moving on several fronts at once, including fusion research, thorium reactors, advanced batteries, and now tandem solar cells. That portfolio approach is important because it means the country is not waiting to see which energy technology wins. It is funding multiple futures at the same time and letting the strongest options rise into the grid. That makes tandem solar especially important, because it fits directly into infrastructure that already exists. It does not require a completely new power system to matter. It just makes the system already under construction more productive. Better panels on the same land, the same rooftops, the same desert solar bases, the same transmission routes. That is a very different kind of breakthrough from one that needs entirely new infrastructure to work. And that is what makes this moment so strategic. China is not simply trying to make solar panels slightly better. It is quietly changing the ceiling on what a solar panel can do, while also positioning itself to mass produce the result faster than the rest of the world. Meanwhile, other countries are still mostly stuck in the slower rhythm of university research, incremental improvements, and supply chains built around silicon's old dominance. There is still a long road ahead. Perovskite must continue proving its long-term stability, its large-scale manufacturability, and its performance outside controlled testing conditions. It also has to win against the practical realities of the market, where price, reliability, and scale often matter more than the most impressive efficiency chart. But the direction is clear. The technology is no longer just an idea sitting in a journal. It is moving toward factories, pilot lines, and eventually real deployment. And that is why the significance of this breakthrough goes far beyond one more solar record. It is not just about a panel that produces more power. It is about a material that can be printed onto surfaces silicon could never reach, a manufacturing model that can piggyback on an existing industrial giant, and a country that seems intent on making sure the next era of solar energy does not belong to a slow-moving global market, but to whoever can scale first. If you step back and look at the whole picture, the pattern is hard to miss. An old scientific concept that once stalled because of cost, instability, and manufacturing limits is being pushed toward completion by coordinated industrial power. The result is not a little improvement at the margins. It is a possible rewrite of what solar energy actually means. Instead of simply being the most common renewable source, it could become the most efficient use of space, the most flexible material for new applications, and the foundation for a much larger wave of electrification. That is why this breakthrough matters. Not because it makes one more efficient panel, but because it may be the moment solar power stops being defined by the limits of silicon alone.